So now listen, differential thermal analysis means we are going to measure the temperature difference between the test sample and an inert reference sample. So previously we were recording the change in the weight with the temperature, or the temperature was maintained constant and the change of weight with the time was measured, and these two parameters, namely the weight change and the temperature or the time, were plotted against each other, and from the graphical representation we were able to explain some of the important physical and chemical characteristics of the substances. In the case of a differential thermal analysis, we are going to measure the temperature difference between two samples. One is the actual sample which we are going to test, and the other one is an inert reference sample. And the temperature difference is recorded continuously as a function of temperature or time. So the heat absorbed or emitted by chemical system is determined. Now you see, if the temperature difference between the sample and the inert reference sample is zero, this means that no physical, no chemical change has taken place. There is no physical or chemical change. If the temperature difference is negative, negative means then you may ask a question, which has to be subtracted from which? Whether the temperature of the sample has to be subtracted from the temperature of the inert reference sample, or inert reference sample has to be subtracted from the temperature of the test sample. Actually, that is why I have put a sign here. You are going to measure the temperature of the sample minus the temperature of the reference sample. That is the order. Because here the sign is going to be very significant. Therefore, it is not merely the difference. It is actually the subtracted value, which has to be put first, which has to be put next. That plays a very important role, because if this sign changes, if it goes wrong, then the entire interpretation will be wrong. So you are measuring the temperature of the test sample minus the temperature of the reference sample. If the sign of the temperature difference is negative, then it indicates that an endothermic change is taking place inside the sample, the test sample, or melting or dehydration is taking place. So it that indicates, that is the temperature difference with a negative sign. I have already told you the order of subtraction. Order of subtraction is the temperature of the test sample minus the temperature of the reference sample. Suppose if you wrongly put it the other way, then what will happen? That will have a wrong interpretation of the sign, which will give you a wrong interpretation of all the physical and the chemical changes that are taking place in the sample. So the order of the temperature subtracting has to be very particular. Test sample temperature minus the inert reference sample temperature. So the delta T will be negative. That negative sign indicates some endothermic change. The endothermic change is taking place. Endothermic change means that includes melting of the sample or dehydration of the sample. If the delta T is a positive, then that indicates it is an exothermic change. So after the completion of the process, what will happen? Again, the delta T will become zero. Because once the change is taking place, once a particular physical change or chemical change is taking place, there will be evolution of heat or absorption of heat. If a temperature is given out, automatically the test sample temperature will be higher than the reference sample. If the temperature is absorbed for a particular process, then automatically the temperature will be greater than the reference sample. So for endothermic change, for exothermic change. For endothermic change, it is negative. Why it is negative? Because test sample temperature is lower than the inert reference sample temperature, because some amount of heat energy is used for the physical and the chemical change. For an exothermic process, what happens? The test sample temperature is higher and the inert reference sample temperature is lower. Therefore, the subtracted value will give you a positive C. So what happens? After the completion of the process, whether it is endothermic or exothermic, once the process is complete, then what happens? The delta T, the temperature difference between the test sample and the inert reference sample becomes zero. So the normal curve for the differential thermal analysis, you will be getting like this. Look here. Let me say this point is a zero. Actually, I have not mentioned here. This is zero. What is zero? This is delta T, the temperature difference between the sample and the reference. This is delta T. So this is zero. It continues in the zero and then it comes down. Once the curve comes down, it is endothermic process. Once the curve goes up, it is exothermic process. So this is how the endothermic and exothermic processes of taking place in a sample has been determined. So this is how you are getting the differential thermal analysis. Now look here. So what are all the important factors in the curve which will give you useful pieces of information? The shape and the size. What is the shape of the graph and what is the size of the curve? They indicate the nature of the test sample. Suppose if it is an endothermic process, there will be a sharp peak, and the sharp peak indicates the phase change, that is melting, fusion, or transition. For an endothermic process, if it is a broad peak, that indicates dehydration going on in the sample, and sometimes some physical changes taking place in the sample. For chemical reaction, normally it will be exothermic. For example, oxidative additions, oxygenation. So for oxidative reactions, the temperature will come out. So it is an exothermic process. So this is the block diagram of instrumentation of uh, differential thermal analysis. Look here, there are two pans. In one pan, the reference sample is taken, and in the other pan, the sample is taken, and this is a very sensitive balance which can measure the weights of the reference sample and the test sample simultaneously, and here is a sensor amplifier. So the sensor will give you the difference between these two samples, and that small signal is amplified, and here is heating blocks. These heating blocks are also connected to a programmer using which you can gradually raise the temperature in a very pre-planned manner, because in all these experiments the temperature change should not be very abrupt. The temperature change should be very slow in rate, which means that per minute you can rise some half a degree or 1 degree, something like this. You should not suddenly raise the temperature to a very high level. So this programmer is kept here to control the heating rate, and then the sensor amplified sensor signals and the programmer signals are fed into the recorder. The recorder will actually draw the graph. Another thing, what are all the different factors affecting the differential thermal analysis? Size and the shape of the sample or the furnace holder. And the other one is a sample holder material. Suppose if you are having a holder, a sample holder, and the material in which the sample holder is made is a corrosive one, then what will happen? At the rise of the temperature, even the pan itself will undergo corrosion, and the corrosion itself is an oxidation. So what will happen? Some oxidative reaction will give you an exothermic temperature. Then that will interfere into the temperature of the sample or the reference sample. So that will affect your entire graph. And then the thermocouple junction, the sensor. The sensor thermocouple junction has to be very sensitive. And then the positions of the sample, the reference, the thermocouple, where the test sample is kept, where the reference sample is kept. Sometimes what will happen, the distance between the heating blocks and the reference sample, and the distance between heating block and the test sample, if they are different, then these two samples will experience a different type of temperature field, thermal field. So that will affect the graph also. So that is why we have written this positions of the sample, reference, and the thermocouple. And very importantly, the heating rate, how fast we are heating. And then the speed and the response of the recording equipment, that is very important, because if the recording equipment is not performing fast and before it records, if the temperature changes, means then a small lag between the response of the equipment and the heating blocks will interfere into the lagging graph representation. So the graphical representation will not be very accurate. And these are all the factors pertaining to the instrument affecting differential thermal analysis. And there are some 6 important factors which are pertaining to the samples taken, that is, sample characteristics. Number one, the amount of the sample. So it depends upon the amount of the sample. And secondly, it depends upon the particle size. And thirdly, it depends upon the packing density. See, why we discuss the particle size? If the particle size is very small, then the surface area is very high. If the particle size is very big, then the surface area is small. So normally the temperature change or the heating is a surface phenomena. So when the particle size is very small, then the heating will be very efficient, and the particle size is very big, then the heating will be less efficient. So even though you are having only one particular type of the substance, depending upon the particle size, it will change. Now you see, another one is the packing density, compactness, which means even we can say it is the density, how together the molecules are packed, whether they are loosely packed, whether they are tightly packed. So that compactness, how they are packed, that also plays an important role. And another one is the thermal conductivity, whether the substance is conducting the heat or it is using the entire heat for its own purpose, the chemical change, the physical change. And another one is the chemical activity, whether the substance is chemically inert or chemically susceptible for certain reactions. So that also plays an important role in determining the sample characteristics. And then the heat capacity. What is heat capacity? It is the amount of heat required to rise the temperature of a body by 1 degree. What is the quantity of the heat energy required to rise the temperature by 1 degree? Suppose if you take water, it has a different heat capacity. If you have a phenol, it has a different heat capacity. So heat capacity is entirely different for different substances, which also plays an important role in the uh, differential thermal analysis. And look here. So this is the DTA of decomposition of a calcium oxalate monohydrate. Look here. Actually, the graphs are put in two different colors. One is in red color, one is in green color. The green color is the DTA recorded for calcium oxalate monohydrate in air. Whereas this one, red colored graph, is the DTA for decomposition of calcium oxalate monohydrate recorded in carbon dioxide environment. And you can see here, I've already told you when it comes down, it is endothermic process. When it goes up, it is exothermic process. In air, the first peak is endothermic, second peak is exothermic, then third peak is also endothermic. In carbon dioxide environment, everything is endothermic. There are three peaks. In the first peak, the loss of water. In the second peak, the loss of carbon monoxide. In the third peak, the loss of carbon dioxide. So look here, in carbon dioxide environment, the removal of carbon dioxide and removal of carbon monoxide, they take place, and all are endothermic processes. But in air environment, what happens? The carbon monoxide then gets oxidized to carbon dioxide because of the presence of the air. So the conversion of carbon monoxide into carbon dioxide is an exothermic process. That is why this second curve, which is found to be endothermic in carbon dioxide environment, is found to be exothermic in air environment. Now this is called a combined DTA and Tga curve. So what we are doing, we are combining the differential thermal analysis graph and the thermogravimetric analysis graph altogether and put it on the same graph sheet. So look here, actually the green colored one is TGA, the red colored one is the DTA. You can see there is a weight loss at this point, and there is another weight loss at this point, and there is another weight loss at this point. And in all these three places, there is a drop down. There is an endothermic process, a drop down in the temperature difference between the sample and the reference. So look here, actually in the first endothermic process, there is a weight loss of some 12 to 30%. This corresponds to the loss of water. And in the second endothermic curve, there is a weight loss for some 18%, which is due to the elimination of carbon monoxide from the sample. And the third curve, there is a weight loss for 29.93%, and this is because of the elimination of carbon dioxide molecules. Now look here, you take copper sulphate pentahydrate. Copper sulphate pentahydrate, it is a very peculiar compound on heat, which on heating loses its water molecules one after the other. Very slowly it loses. Look here, the loss of two molecules of water from its crystal. Actually, these five water molecules are called water of crystallization. Actually, these water molecules are found in the molecule itself. The copper sulphate is blue colored just because of the presence of the five water molecules. So at 100 degrees centigrade, it slowly loses its water molecules. And this change goes up to 180 degrees centigrade. So in this region, there is an endothermic curve. And then at this point, it becomes copper sulphate trihydrate. And again, another two molecules of water are getting eliminated from the molecule, which starts at a temperature 250 degrees centigrade and it continues up to 275 degrees centigrade. And then what you are getting is a copper sulphate monohydrate. So there is another endothermic curve. And then when the system reaches 300 degrees centigrade, it becomes anhydrous copper sulphate. So this is the combined TGA DTA curve for copper sulphate pentahydrate. Now, the applications of the DTA, it is having fingerprints for various substances because no two substances will have the same DTA curve. So it can be used for qualitative and quantitative analysis. And also the characteristics of polymeric materials can be very accurately known using the DTA. And also in the pharmaceutical companies, the purity of the drug samples or the quality control in cement, soil, and glass industries. The DTA is finding its application. And the heat of reaction or a specific heat or energy changes accompanied with any process can be studied thoroughly and very accurately with the help of differential thermal analysis. And also, in the case of coordination complexes, ligand stability, whether the ligand is stable when it is separately present, or whether the ligand attains extra stability when it is present in the coordination sphere, and how it is bonded, and all these things, that is the ligand stability characteristics, can be studied using differential thermal analysis. So these are all the important applications of differential thermal analysis. Now, if you have any doubt, please ask me. Otherwise, I will pass on to the other topics. I will pass on to other topics. If you have any doubt, please ask me. If you have any doubt, please ask me.